So I would like to also thank the organizers and to Barbara for inviting me again. This has been a fantastic workshop. I think I can go away from this workshop finally understanding what a receiver function actually means. I'm going to talk today about some diamonds that are actually from the sublithosphere, but I think are tracking processes that are important for understanding the lithosphere-asthenosphere boundary, and maybe relate to some of the processes that we've been discussing over the last 2 days. Hopefully that's the case. So where do diamonds form? I think we all know that. They form, or where they found, actually. I think I had form and I changed it to found, because where we find them doesn't necessarily relate to where they form, because we find them associated with cratons almost uniformly. And that has to do with really what's bringing them to the surface, and that's kimberlites. So there's this connection between where we find kimberlites, and that's in old cratonic lithosphere or surrounding cratonic lithosphere, and that's where you have the opportunity to sample the diamonds, because the diamonds are coming from deep, and kimberlites are deep-seated melts. So the real question is, why are kimberlites associated only with cratons? And that's a question I won't be addressing, but perhaps might come back to it and have some speculations in that regard. So we're going to be looking at some diamonds, and importantly, the inclusions in the diamonds, and what those inclusions, and these are mineral inclusions, what they can tell us about the processes that are happening at depth. So where are diamond source regions? We all know that most diamonds come from the lithosphere. So something like 99% of them, if you have diamond jewelry today, that's very likely a lithospheric diamond. So here's a nice diagram by Tom Stockel showing the graphite to diamond stability fields, and that in the base of cratonic lithosphere you have the pressures required to stabilize diamond. And so again, most of the diamonds that we have come from that region, and sometimes they have mineral inclusions, and those mineral inclusions can tell us something about the processes. For example, they've been excellent as probes of the lithosphere. This is some work by Steve Chaire, and what they noticed for the Koppval craton was that if you look at the type of inclusions, and there's two broad types of silicate inclusions. Ones are identified as P-type or peridotite type inclusions, and another family which are so-called E-type or eclogitic inclusions. And what they noticed is that if you look at all these different pipes, that there's a clear correlation between P-type inclusions and fast lithosphere, and conversely, slow lithosphere and eclogitic type inclusions. And this led to a model of this sort of agglomeration of slabs of material onto the lithosphere, onto perhaps a core, an old cratonic core, and then surrounding that eclogitic material. What they also found in terms of dating the inclusions in diamonds, so these are rhenium-osmium dates from sulfides, is that you see a clear distinction between older peridotitic diamonds, which go all the way back to about 3.4 or 3.5 billion years, but you never find eclogitic ones that are that old. They stop pretty much abruptly at around 3 billion years, and they interpreted that as representing perhaps the onset of subduction around the craton, perhaps the onset of subduction-style plate tectonics as we know it today. So that's an example of how they've been used in the lithosphere. I'm not going to talk about the lithospheric diamonds anymore. Instead, we're going to look at much more rare diamonds, and these make up, again, only about 1% of the population, and of that 1% of the population of diamonds, only a very few of them have inclusions. So these are quite rare, and they come from a wide range of depths, some of them as deep as the lower mantle. And I'm going to talk to you today about diamonds from Brazil that give indication for having originated in this entire pressure range and have been transported from the lower mantle up to the base of the lithosphere. And in my view, are recording and tracking processes involving subducted material and low-degree partial melts in this region. To understand the processes I'm going to be talking to you about, we need to understand about diamond stability. And one of the most important aspects of diamond stability is oxygen fugacity. And so I'm going to have just a very short tutorial about what we think we know about the oxygen fugacity of the mantle. So here on this, on the y-axis, we have log of FO2 relative to the phayolite magnetite quartz buffer. And here we have pressure. And these are estimates of the FO2 from xenoliths, from craton, Slave, Kotval, Fennoscandian, and Udachnaya, I believe. And what we see is that when we calculate the FO2 from these xenoliths on the basis of this reaction up here, what you're looking at is the formation of the skiagite component, or an Fe3+ rich component in garnet. So this is phayolite plus ferrocilite goes to skiagite. And so you can have an activity model for that reaction. You can analyze your sample, your garnet, for Fe3+, and you can calculate an FO2 if you've calibrated that. So this is the in-member equation, and we see that the slope that we calculate for the actual xenoliths is lower in FO2, and that's because in the real system we have other things which are diluting the activities, like magnesium. Okay, but what the bottom line from this diagram is, as we go deeper and deeper to higher pressures, the FO2 decreases in the cratonic lithosphere. And this is simply because we're dissolving Fe3+ into garnet. Garnet really likes Fe3+. As you increase pressure, the volume change of this reaction is positive, as it's written. So with higher pressures, it wants to go in this direction. Eventually, garnet wants that so much that it will, that's the wrong diagram, I'll show you later. It will start to scavenge Fe3+ from FeO and make an iron metal, or an iron nickel metal phase. Okay? This also happens in the lower mantle, where silicate perovskite, magnesium perovskite, sorry about that, also has a very high preference for Fe3+ in its structure, primarily through this exchange reaction involving Al3+, so much so that, again, FeO in the minerals will disproportionate to provide that Fe3+ and make a free iron metal phase in the mantle. And under those conditions, the mantle is then very reducing. This is for a constant oxygen content mantle. Okay, you just take a piece of mantle, primitive upper mantle xenolith, measure its composition, and then if you take that and increase pressure, FO2 will continually reduce until you're all the way down to about iron woostite. So that leaves us with this kind of a model for the mantle FO2 structure. That is presuming that cratonic lithosphere is giving us some indication of what the asthenosphere is like. We don't have samples of the asthenosphere, of course. But the idea is that the upper mantle is relatively oxidizing, around FMQ or a few log units below that in the very shallow upper mantle. We know that from abyssal peridotite and from basalts. But as you go deeper, you become progressively more reducing. By the time you get into the lower mantle, it's a very reduced system, most likely with free metal from the transition zone on down. Okay? Now that's important when we start to think about how diamonds form in the sublithospheric mantle. Just to hammer that home a little bit more and to develop a further appreciation of why this is important, here's a diagram. This is actually a diagram drawn by Dan Frost. Again, delta log FO2 relative to the FMQ buffer, so FMQ would be up here. Pressure, xenoliths here again. And what I want to draw your attention to is this diamond CO2 melt line, okay? Because that's going to really, in the mantle, it's going to define how carbon, what species carbon is going to be in. Is it going to be diamond as a carbon species, or is it going to be oxidized? And if it's oxidized, it's going to lower the solidus a lot, and it's going to want to be in a melt form. It's going to want to be carbonate melt. Okay, so it's really a solid carbonate melt equilibria that's important, and you can imagine that if you have a mantle which is upwelling, it's got diamond in it, if it hits that line, if the FO2 is changing and if it hits that line, all of a sudden the carbon is going to become oxidized through this reaction. Your carbon is reacting with the Fe2O3. Remember I said you want more Fe2O3 in garnet as you go deeper. Well, as you're coming shallower, it's giving up its Fe2O3. And at some point, and as it's doing that, it's eliminating all that free iron that was made. And at some point, it's going to start giving oxygen to the carbon. And as soon as it does that, you lower the solidus by hundreds and hundreds of degrees. And that's called redox melting. Okay, so you suddenly have some free CO2, and you make a carbonate phase, lowers the solidus, and you start melting. Okay, and so this is a really nice diagram in a recent paper by Stagno et al. And this is kind of how you might view the asthenosphere beneath the mid-ocean ridge then, that there are diamonds we would expect in the mantle. We don't ever see them because we don't have a kimberlite that's down there that's coming up and sampling those. But it's very likely in ambient mantle pretty much everywhere, if there's some carbon beneath about 200 kilometers, it's going to be in the form of diamond. And it's not until you get to around, in their model, around 150 kilometers, and it will depend on the amount of carbon in the system and the buffering capacity of the system, but this is where you have a redox melting front. And so you produce this apron of low-degree melts but below, for example, a mid-ocean ridge. This would be the high-degree melting zone, and here you'd have low-degree melting due to this redox melting phenomenon. Now, the opposite of that is redox freezing, all right? And this is where diamond formation in the sublithosphere comes in. This is by a paper from Rohrbach and Schmidt, and this is sort of the in cartoon of an experimental paper where they've shown that this is really what happens. And on these right panels over here, you have, again, FO2 relative to iron woostite in this case, rather than FMQ. And over here, you have the percent of metal in the system, okay? And you can see as soon as you get deep enough to where you've exhausted all of the oxygen in Fe3+, and it starts disproportionating, then you start getting metal in the system. So you go into the transition zone, you start producing more and more metal. By the time you get to the lower mantle, you've got a full weight percent almost of metal in the system. And that gives the system a certain buffering capacity. Now, the idea here is that if you, for example, take subducted material, which is oxidized into the deep mantle, and you heat this, and maybe you have a stagnant slab, you have a buoyancy inversion, the slab lays out for a while, heats up to its carbonated eclogite melting point, then those oxidized carbonate-bearing melts will infiltrate and basically metasomatize in the transition zone. And when they do that, it'll go into a very reducing environment with plenty of buffering capacity to strip all of that oxygen from that CO2 and convert it into Fe3+ into garnet. Then you'll make diamond, and that's a redox freezing process. So it's the opposite of the redox melting that occurs at shallower conditions. So what I'm going to try to show you is that we see this process in these sublithospheric diamonds, and that we can actually track a process like this that's happening all the way from this region to the base of the lithosphere. So the diamonds I'm going to be telling you about are from the Juína region in Brazil. This is a famous region for sublithospheric diamonds, specifically two kimberlite pipes, Collier 4 and Juína 5, which are located just at the southern end of this part of the Amazon craton, just within a mobile belt. In terms of where the base of the lithosphere is, this is some work by Feng et al., and these are S-wave tomography models. And for me, I like these nice colored blobs where I can stand back from a long distance and say, okay, yes, that's the base of the lithosphere. And they put it at around 160 kilometers. Clearly, one thing I've learned is that's not that easy to do at this meeting, so 160 plus or minus something. But it's going to be close to that level, I think. Excuse me? It's a checkerboard test. Okay. For someone like me, it's like, yeah, that's the base of the lithosphere. Another checkerboard test for you all to look at. This is MT data from this isn't quite from, so we're up here actually, but this is close to the San Francisco craton. There's been a number of these MT studies. This is just one of the older ones, but again, you get the sense at the base of the lithosphere, I guess, is somewhere in this region, around 150, 160 kilometers. Okay, so the diamonds themselves. Here's an example of what they look like. These are cathodoluminescent images, and I should have put one of maybe a typical lithospheric diamond, because they're much more uniform and kind of blah, where these guys have clearly lived a relatively tortured life. They're highly zoned. This particular one here, for example, shows multiple nucleation sites. It has indications of resorption, again, multiple nucleation and resorptions in its history. And here we have sector zoning, again, of a core, clearly several different phases of growth, and sometimes resorption in these diamonds. I should also mention that unlike lithospheric diamonds, the sublithospheric suite are almost uniformly type 2 diamonds. That means they have undetectable nitrogen, basically, by FTIR, where most of your lithospheric stones have 100 or 200 ppm nitrogen. I won't talk a lot about carbon isotopes, but I just want to implant in your mind that these diamonds are forming, in our view, from recycled material. So this is some work by my student Andy Thompson on a large suite of stones from the Juina 5 kimberlite. And so what you see here is del C13 relative to some carbonite standard, which would be at 0. The distribution here in red is the global distribution of diamonds. Most of those are lithospheric stones, and you see this very distinct peak at around -5, which is typically called the mantle value. These super deep diamonds or sublithospheric diamonds from Brazil in these two pipes tend to be much lighter, especially from the Juina 5 kimberlite, where we have a big peak over here at around -25. And while this is quite controversial in the literature, our view is that this reflects recycled carbon. So this is subducted, possibly biogenic, possibly just organic from Fischer-Tropsch type processes in the crust related to hydrothermal circulation. But this is subducted carbon coming down in an eclogitic portion of the slab. Now, I think that largely because of the nature of the inclusions that we find. Okay, so here are a suite of a variety of different kinds of inclusions from these diamonds. And first of all, notice how small they are. Okay, so they're very, very tiny. And we take the approach of painstakingly polishing in through these diamonds until we expose them. So in early studies where you broke the diamonds apart to find inclusions, you would never, ever see these guys. Okay, so what we do is we look by confocal Raman and try to identify them within the stone and then polish down into them with a diamond polishing wheel. It's not something I've ever done. That's what students are for. And they've exposed, Andy's been fantastic with this. He's a real, if he doesn't get a job in academia, he can go to, Amsterdam and get a job as a jeweler, I'm pretty sure. He's exposed this suite here, and we have multiple examples of these. And I think what must be apparent to you is that these are not single-phase inclusions. These are composite inclusions, okay? And our interpretation of this is that these weren't trapped as rocks, but these were once single-phase inclusions that have now exsolved into multi-phase inclusions. That means they have some polybaric history. Okay, so they crystallized as a single-phase inclusion, they were uplifted to another pressure, and they exsolve phases. Okay? Now, when we do our best to analyze these things and reconstruct their compositions, it turns out that they have stoichiometric compositions. This is a titanium-rich calcium perovskite when you put it back together. This garnet in CPX is a majoritic garnet. These two here end up with a perovskite stoichiometry. So we've interpreted them as iron and alumina-rich perovskites, the kind of thing that you would find in subducted eclogite. And these two here, one of them is a so-called CF phase, which is a high-pressure phase stable in eclogite in the deep transition zone or upper part of the lower mantle. And this is an NAL phase, again, another phase which has only been produced experimentally in eclogitic type compositions at lower mantle conditions. So our interpretation is that these things formed in the deep transition zone or the upper part of the lower mantle. Okay, so if you just look at a phase diagram and you kind of sprinkle these onto the phase diagram, this is for subducted oceanic crust. This is a CF field, the NaL field, magnesium perovskite, calcium perovskite, garnet. We have CPX, we have stishovite as well, and these clinopyroxenes. So we have the whole pressure, we have the whole phase diagram basically in these diamonds. It's quite outstanding. But I want to get the impression, I'm going quite slow, of the polybaric nature. So if you look at majoritic garnets and use a calibrated pressure scale for these, what you find is that for a wide variety of sublithospheric locations, you get a wide range of pressures throughout the deep part of the upper mantle and the transition zone. These are another pair of exolved phases. This is from a study by Ben Hart. But also in our suite, we sometimes find them where they form as single crystals rather than composite crystals. And when we look at those pressures, we end up getting something around 170 to 200 kilometers. So that looks to us like they formed at the base of the lithosphere. Now others look like they exolved at about the same pressure, okay? Because we can use their exolved compositions to determine what the pressure was of exsolution. And they also give a pressure of a depth of around 170 to 200 kilometers. These are also eclogitic in composition. These are not peridotite type garnets. They have very high calcium contents and virtually devoid of chromium. Okay, so these again formed in some sort of recycled component is very important in their formation. Now I want to talk a little bit about these calcium perovskites because they're the ones that are, in terms of their chemistry, are really giving us some information. Again, these are very titanium-rich perovskites, and if you look at the phase diagram for these, so this is CaTiO3, CaSiO3, based on where they would have been single crystals, that means they must have formed at a depth of at least 250 or 300 kilometers, but their unmixing pressures again, or their unmixing depths again, like those majoritic garnets, are giving something like 170, 180 kilometers, which means they ended up at the base of the lithosphere. So they form deep, they end up at the lithosphere-asthenosphere boundary.
5 minutes.
Yeah, 5 minutes, okay, good, perfect. If we look at the chemistry of these calcium perovskites, they're just amazing because they're tremendously enriched. Now, calcium perovskite is a mineral that is kind of a garbage can for trace elements anyway. It's got a very open structure, it likes trace elements, but these guys are well over the top. So this is, 10,000 times primitive upper mantle. If you had this calcium perovskite as a piece of solid mantle or solid eclogite even if it was at 1 weight % of the total, it would completely swamp the budget of trace elements and would be more enriched than anything you would think about subducting into the mantle. So as a geochemist, when you see those kind of enrichments, you immediately think small degree melt, okay? Because that's where you have very enriched things. So what we did is we said, well, what kind of a melt would produce a calcium perovskite with that pattern? And you can do that if you know partitioning coefficients, and those are available in the literature. And so we calculated those, published this in a 2008 paper, and this is the kind of melt that would crystallize that calcium perovskite. And what you find is that, our interpretation of this, because it's depleted in large ion lithophiles, but not really depleted in high field strength elements or rare earth elements, is that's the kind of thing that you would expect for melting of carbonated eclogite at depth. This is an eclogite that's been through the subduction system. It's gone through dehydration, which strips off the large ion lithophiles, but it retains high field strength elements and rare earth elements in minor phases such as rutile and epidote minerals. So we called this a primitive carbonated melt of subducted eclogite. Now we can take that farther. Here's a whole range of trace element patterns for calcium perovskites that we found from Juina 5. Okay, so they're not all so enriched, and they have different patterns. And we wondered, what does that mean? And one idea we had that, well, if these melts are coming off of a slab, and they're metasomatizing and percolating through, and then they're going to be going through a reactive transport process. They're going to be crystallizing and differentiating. So we thought we'd sort of attempt to model that process. I'll go through this very quickly. So you take a most enriched perovskite, you calculate the liquid that would be in equilibrium with it. This band kind of reflects some uncertainty in the partitioning coefficients. Then you say, this is our model processed morb, the thing that we think was subducted. And then we can invert that liquid to what the solid would have been through that equation. And when you do that, it's not that bad of a match. There's a bit of a mismatch on the heavies, but overall, we're pretty convinced that these are primitive melts coming off of subducted eclogite deep in the transition zone or the upper part of the lower mantle. We can take that even further. So these are melts. This is the most enriched calcium perovskite melt. This is the less enriched calcium perovskite melt, and this is the melt you would calculate to be in equilibrium with our majorites. Because if the calcium perovskites are forming by crystallization from a carbonated liquid, maybe the majorites are as well. And what we find is that if you take that melt and then you start crystallizing calcium perovskite from it, sort of a liquid line of descent, we can easily reproduce the least enriched calcium perovskite. And then another 8% crystallization does a pretty good job with the majorite. We're a bit off down here, but we can probably find a way to do that. So the point is that we at least are convincing ourselves that we're seeing either a reactive transport process, we're seeing differentiation of carbonated liquids at depth, and we're seeing polybaric crystallization of these inclusions in the sublithospheric mantle. So what does all this mean? We end up having some kind of a diagram, some cartoon that looks like this, where we've got subducted slab, which is ponded just at the top of the lower mantle or into the transition zone. You heat up, you form a carbonated eclogite melt. Maybe it's hydrous and carbonated. That material goes off into the very reducing mantle, and those melts crystallize the diamond by redox freezing, and at the same time, through processes most likely of reactive transport and metasomatism effectively, are producing and crystallizing the phases that are being trapped. You're not trapping bits of the ambient peridotite. You're crystallizing minerals, and my student Andy also is working on reproducing that experimentally. And he's got some fantastic results that I don't have time to show you. Now the question is, how do we get from here to here? Because what's happening is we're parking these things up here, and there's some relationship also then with perhaps the kimberlites, because we've managed to get one date from these diamonds. It's very hard to date these things, but we've got one uranium lead date from one of these calcium perovskites, and it gives an age of 105 million years. So it's very young, unlike lithospheric diamonds, which are almost all billions of years old. The kimberlite itself is 93 million years old. Okay, so they're associated in space and time, which to me means that there's some sort of metasomatism going on at the base of the lithosphere that is probably associated with this subducted slab from which all this stuff is being produced in the first place. Now, there's a model by Richard and Iwamori, a dynamic model, which suggests that when you take these possibly hydrous carbonated melts and impregnate them into this region, that you produce dynamic instabilities, and you can actually have small plumes that start shooting up from this stuff. And that's one way to do this, is to get those things up to the base of the lithosphere that way. And as they go, there'll be redox freezing and redox melting as they go, depending on the very local environment, which may explain the complex structures that we see in the diamonds as well. We have one diamond that has a core with a calcium perovskite that must have formed at depths greater than 300 kilometers, but on the rim, it's got a majorite that formed at 170 kilometers. In one diamond, we can clearly see that kind of a depth range with at least two growth episodes showing that they grew at different pressures as well. So I think I'll leave it there and say that this is a very active region and is probably all starting much deeper in the mantle. And that's it. Thanks.